When Michio Kaku finally responded to the latest revelations from the James Webb Space Telescope, the scientific community held its breath. For weeks, astronomers and cosmologists had been analyzing a mysterious new image captured by the telescope, an image that didn't just question current models of the universe, but threatened to upend long-standing beliefs about galaxy formation and the very nature of time. Kaku, a theoretical physicist known for his work in string theory and for making complex science accessible to the public, had remained noticeably silent as speculation swirled. But with his voice now entering the conversation, the scope of the telescope's discovery began to gain stunning clarity. The image in question wasn't just another breathtaking view of the deep cosmos. It was something far more puzzling, an ancient galaxy, or what appeared to be one, located so far away that its light had taken over 13.5 billion years to reach Earth. That alone wasn't entirely unexpected. What truly shocked scientists was the galaxy's size, structure, and surprising level of maturity. According to current cosmological models, a massive and well-structured system of stars like this shouldn't exist so early in the universe's history. The dominant lambda-CDM model, which underpins modern cosmology, predicts a gradual emergence of cosmic structures, meaning that the deeper we peer into the past, the more chaotic and undeveloped those structures should appear. Yet here was a galaxy that seemed fully formed, with spiral arms, mature star populations, and even indications of a central bulge, features that typically require billions of years to develop. Kaku's remarks opened the door to deeper speculation, building upon a discovery that had already shaken the foundations of cosmology. With his signature mix of imaginative thinking and scientific rigor, he suggested that what we're witnessing may not just be an unusual galaxy, but possibly a fracture in our current understanding of how time and space evolved in the early universe. The implications are profound. Either our entire timeline of galaxy formation is fundamentally flawed, or new physics, perhaps involving undiscovered dimensions of reality, may be at work. The James Webb Space Telescope, launched with the ambition of probing deeper into the cosmos than ever before, had already amazed scientists with its unprecedented sensitivity and resolution. But this particular image marked something else entirely, a direct challenge to the limits of what the scientific community believed was even knowable. Kaku described the discovery not as a mere anomaly, but as a paradigm-shifting data point, one capable of sparking a revolution in cosmological thought. The moment evoked past scientific upheavals, like the revelations from Galileo's telescope or Edwin Hubble's discovery that the universe is expanding. Just as those breakthroughs reshaped humanity's understanding of its place in the cosmos, the Webb image now appeared poised to redraw the very blueprint of cosmic evolution. What makes this discovery especially compelling is the way it disrupts the temporal framework of cosmology itself. If fully developed galaxies existed just a few hundred million years after the Big Bang, then the accepted timeline of the universe's evolution must be fundamentally re-examined. Kaku raised the possibility that our understanding of time itself, particularly in the context of early cosmic inflation and matter clustering, may be incomplete. Some speculative theories, including elements of string theory and brane cosmology, propose that the early universe experienced processes that dramatically accelerated the formation of large-scale structures. Once seen as fringe or purely theoretical constructs, these ideas are now entering serious scientific discussions, propelled by what Webb has revealed. Kaku's reflections carried the weight of this cosmic uncertainty, hinting that the universe may be far more intricate and exotic than previously imagined. The discovery could point to unknown variables shaping the early cosmos, dark matter behaving in unexpected ways, the influence of dark radiation, or exotic particles that triggered rapid galaxy formation. Certain models even challenge the cosmological principle, suggesting the universe may not be uniform on large scales, but instead contain pockets of accelerated evolution, driven by localized conditions or ancient quantum fluctuations. If these phenomena are real, their implications extend far beyond astrophysics, challenging core assumptions in particle physics, quantum mechanics, and the very fabric of reality itself. At such a pivotal moment in science, the power of visual evidence cannot be overstated. The image from Webb is more than just a dataset. It stands as a visual contradiction to the standard model. Where previous telescopes offered glimpses or partial confirmation of early galactic structures, Webb has provided unprecedented clarity, thanks to its remarkable resolution and infrared sensitivity. The features of these ancient galaxies can now be studied in extraordinary detail. Kaku emphasized that the telescope's ability to detect redshifted light with such precision is what makes this moment truly transformative. For the first time, humanity is witnessing the universe as it appeared during what should have been its chaotic infancy, and yet, what we are seeing appears strangely mature. This cosmic discrepancy raises profound questions. Is our interpretation of redshift truly accurate? Could some unknown process be mimicking the effects of vast cosmic distance? While most astrophysicists remain confident in the redshift-distance relationship, Kaku entertained the possibility that undiscovered forces or quantum effects might be subtly distorting our measurements. He stressed that scientific breakthroughs often emerge not from ignoring anomalies, but from confronting them head-on. In his view, this single image could represent the first step toward a deeper, more expansive understanding of the universe, one that reaches beyond the boundaries of classical cosmology. The psychological impact of such a discovery is also significant. Scientists rooted in long-standing models may struggle to fully process the implications of evidence that defies so much of what's been accepted. Yet history shows that scientific revolutions often begin in moments of unease. Kaku encouraged his peers to treat this not as a failure of existing theory, but as a rare opportunity, an invitation to rethink what's possible in light of compelling new data. The James Webb Space Telescope was never intended to simply confirm what we already believe, it was built to reveal the unknown. And with this image, it has done exactly that, in breathtaking fashion. The implications of this discovery ripple far beyond cosmology, reaching into other domains of physics. For instance, theories of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, may need to be revised or expanded. If galaxies were able to form earlier and more rapidly than current models predict, perhaps inflation seeded a more structured framework for matter to coalesce around. Alternatively, gravity itself may have behaved differently in the early universe, or other fundamental forces may have worked in tandem to accelerate galactic development. Kaku, a longtime proponent of multidimensional models of the universe, sees this discovery as a renewed opportunity to explore those ideas. One especially intriguing possibility is that this galaxy, and others like it, might not even be entirely native to our universe. Kaku floated the speculative, yet mathematically grounded idea that the James Webb image could offer indirect evidence of interactions between our universe and other brains within a higher dimensional space. Within this framework, collisions or interactions between brains could inject matter and energy into our universe, speeding up the formation of cosmic structures. Although radical, such ideas are gaining traction as observations increasingly diverge from classical predictions. From a technological perspective, the James Webb Space Telescope is a monumental achievement, the result of decades of engineering innovation, international collaboration, and scientific vision. Its instruments are not merely more powerful than those on the Hubble Space Telescope, they represent a generational leap forward. By observing in the far-infrared spectrum, the telescope can penetrate cosmic dust and capture images of galaxies and stars in their infancy. This capability allows scientists to analyze the chemical makeup of these ancient systems, providing vital clues about the processes driving their formation. Most importantly, Webb enables a form of cosmic archaeology, reconstructing the universe's earliest chapters not just through theory, but through direct, unprecedented observation. Kaku's discussion also highlighted the philosophical implications of this discovery. If the universe is stranger and more complex than we ever imagined, what does that mean for our place within it? For centuries, humanity has gradually moved away from the notion that we occupy a central position in the cosmos. Each scientific breakthrough has revealed a vaster, more indifferent universe. Yet, the discovery of these ancient, mature galaxies may suggest something different. Not centrality, but connectedness. Perhaps the universe is not a singular isolated event, but part of a larger, interconnected multiverse, and our understanding is only now beginning to catch up with that profound reality. If you enjoyed this video, please give it a like and subscribe to our channel. Also, leave your comments below to share your thoughts on Michio Kaku's reaction. What do you think the James Webb Telescope has revealed? We want to hear from you. Thank you for watching, and see you next time.